wondered why your remote sensing analysis just isn't working out the way you want it to?
Are you fed up with your GPS points not matching up with your Landsat image?
Can't quite find the right remote sensor to monitor your agricultural plot? Well, we've got the answer for you. What? Introducing the methodological guides to select an appropriate grid resolution for output maps based on the essential characteristics of the input data.
With raster-based GIS, grid resolution controls many aspects of remote sensing using for mapping. If you want to find out the right pixel size for GPS positioning, but the scale of your project is unknown or non-standard, then you can access this by analyzing the mapping methodology.
To ensure this, we first need to estimate the confidence radius, which is the radius of a circle where we expect most of the points to appear, where p equals 95%. Where r squared e is the average error radius and the p is the grid resolution, the recommended grid resolution is the one where 95% of the points would fall within the pixel.
For example, if we have 100 GPS points, an average error of 8.5 meters, standard deviation of 5.2 meters, and with this equation right here, we would get a suitable grid resolution of 36.6 meters. With this grid resolution, 95% of the GPS points will fall within the right pixel and correspond with the Landsat imagery of your choice.
Another method that can be useful in determining appropriate grid resolution is point data interpolation. If you have point samples collected in the field and want to make predictions, your mapping products should have an equal density of samples per area. This is your inspection density. If dealing with regular point samples, the formula P equals 0.5 times the square root of A over N, where A is the surface of the study area in meters squared and N is the total number of observations. For example, using soil mapping applications, when we have 553 profile observations, where the area is 12.1 kilometers squared and the sample density is 45 observations per square kilometer, and the closest point pair is 120 meters and cumulative distribution is 95%. Using this formula, the grid resolution comes out to be between 5 to 150 meters. It's difficult to assign a suitable resolution for terrain analysis because there can be a significant difference between the surface elevation on a coarser grid versus the actual topography. So the suitable grid resolution can be derived for given sample elevations and based on the complexity of the terrain.
Here is a schematic example showing the effect of grid resolution on the representation of topography. 2 coarse of a grid resolution, where pixel size is 2.5 meters, will misrepresent topography, whereas finer grid resolution of pixel size 0.5 meters will be more effective in representing all peaks and channels.
In 2D topography, it can be estimated from the total length of the contours by using the formula P equals A over 2 times the total cumulative length of all digitized contours. The total area is 30.69 kilometers squared and the elevation is 80 to 240 meters. The contour lines is 127.6 kilometers and the average space between the lines is 107 meters. So therefore, the grid resolution comes out to be at least 553.5 meters. In terms of grid resolution and cartographic concepts, your pixel size is going to be determined by the maximum location accuracy, the MLA, or average size area, ASA. Your MLA and ASA can be used to estimate the suitable grid resolution for a given map scale. Now, I shall demonstrate how to select a remote sensing sensor based on the size of agricultural plots. It is important to know 4 grid cells is considered equivalent to the minimum legible delineation, the MLD, which is the smallest size area that we map. For example, the MLD is 25 centimeters squared, can be estimated based on the scale number, SN, where P is the grid or pixel size and MLD is the minimum legible delineation area on the ground in meters squared. This means that for a 1 to 50K scale, the MLD is 6.25 hectares and the suitable grid resolution is 125 meters, which seems fairly coarse.
The grid resolution can also be related to the MLA, which commonly ranges from 0.25 millimeter to a maximum of 0.1 millimeter on the map. So for a 1 to 50K scale, the smallest legible grid resolution is 12.5 meter.
We're using a polygon map that has 122 polygons. So the average size polygons is 0.824 hectares, and that has a standard deviation of 1.005 hectares. And when we apply the 5% inverse cumulative distribution, it results in 0.0046 hectare. And as a result, the pixel size would become 20 meters, and the coarsest legible grid resolution is 70 meters.
Another method that can be used is finding the grid resolution based on computer processing power. The grid resolution can also be related with the size of area and processing power of our computer. Fundamentally, the calculation time will increase exponentially, which is cubically, with the total number of pixels in a map. Lagasheri and McBratney discussed the relationship between the grid resolution and processing capabilities of standard desktop PCs and discovered the following rough relationship between the log of the image size and the current year, where log 10 meters is the logarithm of the image size in pixel and y is the current year. According to this formula, the standard image size in year 2005 would be about 10 to the power of 7 pixels, which makes it an image of 3000 by 3000 pixels. The grid resolution can also be estimated by dividing the size of the study area by the number of pixels that a computer can handle.
There are 3 grid resolutions that can be derived from your input data. The first is the coarsest legible grid resolution. This is the largest resolution that can be used given specific scales, accuracy of positioning, object size, and the complexity of terrain in order to maintain the accuracy of your input data.
The second is finest legible grid resolution. This is the smallest grid resolution that can represent 95% of spatial objects and topography. It is the finest meaningful resolution that can correspond with the concept of maximum location accuracy, which we find with our GPS.
Lastly, we have the recommended grid resolution. This is a compromise resolution that uses numbers between the finest and the coarsest grid resolution.
It is important to know not to use grid resolutions that don't comply with the properties of your input data.
In the market, this guide costs $3,000, but if you call now, you can get it for 4 easy payments of $123.45. That's $123.45. There is no right pixel size that can be applied to all projects.
But finding the right pixel size can be determined by your project's variables and objectives.
There is no right pixel size, but we can help find the one that's right for you.